It's always shockingly difficult every week. Here we go. Still struggling, just one sec. There we go. All right. So, thanks for coming. So I'll slowly get started. Just very briefly today, recapping last time and then telling you what we're going to talk about today. So we discussed the short Zipple lemma, which basically just says that any two low degree polynomials, even if they're multivariate polynomials, disagree almost everywhere unless they're the same polynomial. So specifically, if P and Q are two multivariate polynomials of total degree D, and we discussed last time what total degree means, and P does not equal Q, then if you pick a random input in let's say from any product set, so say S to the M, where M here is the number of variables of P and Q, and S is any subset of the field that P and Q are defined over, and you evaluate P and Q at that point, that random point that you picked. The probability they agree is at most their degree over the size of this set S that each entry of the random point was chosen from. Okay, so again, the message is that if two polynomials have degree like much lower than the space that you're drawing each coordinate of a random input from, and they're not the same polynomial, then if you evaluate them just at a single random point, that's sort of sufficient to ascertain with high confidence that they're literally not the same polynomial. So kind of checking whether two polynomials are literally the same polynomial can be done efficiently in a randomized way just by evaluating them both at a randomly chosen point. Okay, so that's short Zipple. And then we discussed error correcting codes and how they arise in SNARK design. We said a little bit about that. So error correcting codes just map short messages to longer code words. And here ENC is for encoding. And what SNARKs typically need, they don't really need error correction. They need distance amplification. And the idea of a SNARK is if the prover is claiming to have run some computation on a witness, you want to make sure that the prover really ran the computation correctly step by step. And if it sort of made even a single tiny mistake over the entire course of the computation, you want the verifier to sort of pick up on the mistake and reject the proof. And so intuitively what SNARKs need is something that will take tiny errors or deviations, between messages and blow them up into very, very easily detectable differences. And that's exactly what error correcting or distance amplifying codes do. Now, the term error correcting codes can get a little confusing in the context of SNARK design, because in SNARKs, typically no error correction is ever done. And the reason being that the honest prover never introduces any errors. So, the verifier, there should never be any errors for the verifier to correct. So that's why I use the phrase distance amplification. rather than error correction. It's like, typically these things go together. Like, it's often the case that if you have a distance amplifying code, that maps any two messages that differ in even like one entry into code words that differ almost everywhere. Very frequently those codes will also have good error correction properties, where if I give you a code word and it's a little bit corrupted, you can actually figure out where the corruptions are and fix them. But in snarks, like neither the prover nor the verifier really ever needs to correct any errors, and that's basically just because the honest prover will never introduce any errors, so there's never anything to correct. Now, another sort of subtle thing to say or to make clear is that often neither the prover in the snark nor the verifier need to ever like materialize the whole code word. Now, sometimes they do, and I'll tell you in a second the handful of times they actually do. But one example that we've seen where no one ever materializes the whole code word is in fingerprinting. Where we had Alice and Bob who want to know, are their input vectors the same vector? And they want to know that they want to avoid just Alice sending her whole vector to Bob. And so, what Alice does is she interprets her vector x as a polynomial p, and she sends to Bob just a random input r to p, and he evaluated at r, and Bob just checks whether so he interprets his input as a polynomial q, and checks whether p of r equals q of r. Right. And so, what's really going on here is, if I were to write down all evaluations of P, in the entire field, say it's a large prime order field or something. So I wrote down, all field size many evaluations of P. Now, this would be called something like the Reed-Solomon encoding, or perhaps the low degree extension encoding of X. Low degree extension encoding. And so, this is an enormous code word, right? It had, if this field has size like 2 to the 128, like no one in the known universe can like write down this code word. It's just way too big. But that's okay. No one ever has to write it down. Like what Alice is doing is she's just picking a single random symbol in this code word and sending just that symbol to Bob. And similarly, Bob is, looking at just that symbol of the encoding of Y. So no one is ever writing down all possible evaluations of P and Q. They're only looking at a single evaluation. That's like one symbol in the low degree extension encoding or Reed-Solomon encoding of X and Y. So the one situation in snarks where people do have to write down the entire code word tends to be in hashing based commitment schemes. And there are some other cases as well, but this is maybe the most prominent and important one, where so things like Fry, Laharo commitment, Binius, these all involve taking some vector that you want to commit to and actually encoding the vector with an error correcting code. And the prover does have to write down this encoding, and then the commitment will often just be something like a Merkle hash of the encoding. And so the commitment is just the Merkle root, something like that. Elsewhere in the snark, outside of these commitment schemes, it's often the case that, the distance amplifying codes are sort of implicitly around, but no one is ever writing down the entire code words. Okay, so that was basically what we covered last time. Let me pause here, see if anyone is asking any questions about the recap or just any random questions you happen to want to ask today.
Hello, sir. Am I audible?
I missed that. Go again.
Am I audible?
Yeah, I can hear you. Go ahead.
So I had this question that earlier when this whole notion was introduced for a d degree polynomial, it was enough to give out d plus one evaluations to correctly commit to that particular polynomial, univariate one, right? So why is it
Mhm.
that in this case we had to move out of giving just d plus one evaluations, but rather giving evaluations throughout the field? Is it because we needed enough distance? Is that the reason why we had to move to such
Yeah,
move?
that's exactly right. That's it. So if you just want to specify the degree D polynomial, degree D evaluations are enough. So um, that's basically the message. So I can the message can be if P is degree D, like a complete specification of P is just like any, if it's a univariate polynomial, is just any D plus one evaluations of it. But I can give you two different polynomials of degree D, and they may differ only in one out of these D plus one evaluations. So, this is like, the distance of just, I'm calling it the message space. If you declared these to be the code words, like the distance would be like trivial, right? It's like as small as can be. Like there are two different quote code words if we call these code words that differ in only a single symbol. So that's why if you instead define the encoding to be a much bigger set of evaluations, so you could have the D plus one evaluations in the message, if it's a systematic code, could still be there in the code word, but then you add redundancy, D plus two up to you can go up to the whole field if you want. You could stop at maybe 4D evaluations. Then you get this property that like any two distinct code words have high distance from each other, two distinct code words. So if you did 4D evaluations, they can agree on at most something like D over however many evaluations there are, 4D fraction of points. So like what their quote relative distance then would be like 3/4. They can agree on so if you don't have any redundancy there, the distance is terrible. That's what's going on. If you add enough redundancy, you get pretty good distance. And that's what distance amplification means. Was that a clear response?
Yes, sir. But then D plus one evaluation was enough to ensure soundness against the malicious prover. Then why is it that, see, this extra information is not amplifying soundness in any way? Just wanted to double check.
No, so it is. It is. So here, the soundness error of this like fingerprinting protocol was the degree of the polynomials, which is like n minus one, over the size of the set that R is chosen from. Which for simplicity, I always just say like the whole field, but it could be a subset of the field. And so if this set was a set of size n or something, if R was chosen just from a set of size n, which is what you're sort of proposing here, if you declare these to be the code words, then the error probability becomes just n minus one over n, which is like really bad. That's like super close to one. Basically, what's happening there is, so again, like I'm sort of proposing the view that this fingerprinting code, fingerprinting procedure is sort of just comparing not X and Y themselves, but comparing a random entry of X and Y's like Reed-Solomon encodings. And if you define the Reed-Solomon encoding to just be, like n minus, like n evaluations of these polynomials, then they're only going to detect a difference if you happen to pick the one evaluation that they differ on. Whereas if you define the Reed-Solomon encoding to be like, have an entry for the entire field, then you're very, very, very likely to detect a difference. Basically, there are n-1 evaluations that they might agree on. So you better choose, a random point in an encoding that has length much bigger than n-1. Does that make sense?
Yes, sir. Thank you.
Can I take a stab at quick reframing?
Please.
So it's kind of a question of like what our sample space is for the random selection that we're doing. And we know that like there's only d points. Let's say d is 10. There's only 10 points where the two polynomials can agree. So the bigger we make our sample space, the lower we make the probability that we accidentally pick one of those points that they agree. So in this case, if you pick your sample space to be the whole field, then you're making that probability really small.
Yeah, that was great. Thanks. Yeah. So, if you just wanted to like specify the polynomials at play here in your example there, you only have to write down 10 evaluations, but then there's a very good chance you wind up picking, one of the 10, just 11 evaluations, but then there's a very good chance you wind up picking one of the 10 at which they agree. But if your sample space is, of size much bigger than 10, there's a tiny chance you wind up picking one of the 10 points that they agree at.
To add to this one, we were talking about domain space as far as I could understand. And could you tell a word or two about the space of the resulting values? I mean, how important is it that this polynomial returns a group element, a bigger group element, or it can be, or would it work not over a group, but just some big bunch of values, for example, and so on?
Yeah, I'd say, with polynomials, especially univariate ones, well, in general, really, the domain and the range are the same. So if you have a univariate polynomial over some field, right, it spits out values in the same field. So if you're right that we need a big domain for soundness reasons, for security reasons. But having a big domain sort of entails a big range as well. I sort of leave it at that. Now, there are limitations in terms of what fields you can work over in certain snarks, and in particular, if your snarks use elliptic curve groups anywhere in the snark. These come up specifically in the commitment schemes. You're sort of forced to use, just due to the nature of elliptic curve cryptography, a field of size at least 2 to the 256, just because the elliptic curve group won't be cryptographically secure otherwise. But other than that, you're sort of free to use a field as small as say 2 to the minus 120, 2 to the 128, if you're targeting roughly like 128 bits of security or something. And we can, I think today is not the time to get into, you'll talk about there's a big focus these days on snarks over smaller fields, much smaller fields. But ultimately, I think that's a slightly confusing or misleading terminology, because ultimately, at some point, these snarks do have to move to a field of size at least 2 to the 128. And so, you're able to keep like a lot of the provers work potentially over a smaller field, but somewhere for security reasons, you're eventually going to have to work over a field of size 2 to the 128, or you're never going to be able to hope for 128 bits of security, at least not without very careful application of some kind of repetition. Anyway, so I think that's the most I can say in response to your question right now. Was that enough?
Yeah, absolutely. I'm just thinking if we even need a field here for this particular one, but it's kind of not grounded thinking.
Yeah, no, that's a great question. Like, do you really need a field, or like, is there such a thing as like a polynomial defined over, like a ring that's not a field, or a group, which are algebraic objects that are not quite the same as fields. And people have looked at that. And what I'll say now is there can be some benefits to that, but most of what's deployed today just works over fields. And over the course of this study group, I'll elaborate on details, but they're way in the weeds at the moment.
Yeah, absolutely. Thank you.
Yeah. Any more questions?
I have a question.
Go ahead.
You said that for the hashing cases, that they needed to do this encoding over all the fields. Does this mean that they need to use like smaller fields or something, or
Yeah,
is
well,
there
so
any
what
other?
they'll do, yeah, great. So what they'll do is if you want to take a vector X and look at its Reed-Solomon encoding, so RS of X is just, Reed-Solomon encoding of X. This means they're interpreting X as a polynomial and evaluating that polynomial at a bunch of points. So interpreting as P, evaluating it at, some number of points. So let's say X has length N, and they're evaluating it at K points. They'll often choose K to be a constant factor bigger than N, like 2N or 4N or something. And then to make sure that the encoding procedure is fast, they'll choose these points to be like very special and nice, like all K roots of unity in the field. And that's what ensures that you can reasonably quickly go from X to its encoding, RS of X. And so it's important here that, so they can still work over, so this can still be, a big field, you say it doesn't really matter size 2 to the 128 if you want, whatever. It's just that the encoding is not going to evaluate the polynomial at all field elements. It'll evaluate only a very special subset of field elements. Does that make sense?
Yes, I remember reading about something like this.
Yeah.
Okay. Thanks.
Yeah. And yeah, so let's see. Yeah, and because I guess the one extra thing I'll add is, because the encoding is only like 2 times or 4 times bigger than the message, the distance, like the relative distance of the code is at best like a half or 3/4 or something, which sort of means the way you can think of it is like every time the verifier were to like inspect a random element of the encoding, there'd be probability like a half or a fourth that it sort of gets unlucky and picks some point that there's agreement where there shouldn't be agreement or something like that. It's like you give me 2 different messages X and Y, and their encodings can agree on up to half or a fourth of the coordinates. And so that's why you see things like people will talk about like Fry verifier queries, and you'll see the number of queries will be like some number L, so that like a half to the L is at most 1 over 2 to the 128 or something. And what's going on is like you have to look at if you have a probability of half of sort of failing to detect a problem on any given query to the encoding, you're going to have to actually inspect like 128 different entries of the code word to have like cryptographically good probability that you actually detect a difference if there is, a difference. Yeah. Okay, more
Okay.
questions?
They do like more rounds like the encoding is not that big, but then they do more rounds.
So
Like more queries.
fortunately, all of these queries can be made kind of in parallel, so it doesn't actually add more rounds. It does make the proofs bigger.
Okay.
With something like Fry, and you'll see this also in like Binius and stuff. The proofs are pretty big, like multiple hundreds of kilobytes or something, something like that. If you set the security appropriately. And it's not lots of rounds, but like the proof size will be like number of queries, times like log squared of the length of the message being encoded. And so, this gets to be pretty big in the end, because in large part because of this number of queries factor here. Yeah. So it's making the proofs bigger, having all these queries. It's not really adding more rounds though.
Okay, just a last thing, because when you do the Fiat Shamir thing, there can be like grinding attacks and stuff, but maybe I'm confusing something, because if that probability is like it's not very low, couldn't there be like some grinding attack or something like that?
Yeah, there can be, it's now understood. Okay, so I want to try to keep this brief, but still say something useful. Okay, so with something like Fry, if you make like 128 queries, it's known that the grinding attacks will require, like time 2 to the 128, like 2 to the 128 like hashes, must be, computed, by any attacker, that's looking for a convincing proof of a false statement, that succeeds with probability close to 1. Yes, once you fiat Shamir this, grinding attacks will exist, but we get this success probability of an attack so small that you have to sort of try to try the grinding attack 2 to the 128 times before you're likely to succeed. And now there are gaps between what's actually formally known about how long the grinding attacks might take, and the best known grinding attacks. There are some gaps if we're talking about something like Fry, and people just sort of assume that the best known attacks are literally optimal, but we haven't managed to prove that in any formal sense. But yeah, so anyway, whether you're running these commitment schemes that involve error correcting codes, interactively or fiat shamiring them to make them non-interactive. It's like these probabilities I'm writing here correspond roughly to like the bits of security, of the resulting protocol. 128 bits of security here if the success probability is like 1 over 2 to the 128. And if you don't use fiat shamir, that's basically the statistical probability of kind of all 128 queries being unlucky for the verifier and failing to detect that the prover is cheating. And if you do apply fiat shamir, this bits of security refers to like how much work the attacker has to do until it succeeds in finding a convincing proof of a false statement. All right, that was pretty rambling, not actually a great response, but hopefully it did add a little bit of color to what's going on in these SNARKs.
No, it was great. Thank you.
Great. All right, thanks for all the questions. Okay, so moving on to what I want to cover today. So one thing I want to cover is univariate Lagrange interpolation. I'll tell you what that is in a second. And then I just want to formally define like interactive proofs and arguments. Okay, and then I think that's it for today. I'll say a little bit about interactive proofs and arguments, and then that'll be it. I think next time we'll move to multilinear Lagrange interpolation. And that's really the last thing we need before actually seeing one of the most important interactive proof techniques, which is the sum check protocol. And so I don't know if we're actually going to get to this next time, but at a minimum, we're going to get out of the way the very last thing we need to discuss before we're able to talk about the sum check protocol. Okay, so let's talk about univariate Lagrange interpolation. So this is we could either describe what this is via the framework or the perspective of error correcting codes, or just directly in terms of univariate polynomials. So let me start with univariate polynomials. So say I am given let's put it this way. Let P be a degree D polynomial, univariate polynomial. And say I am given like as input D+1 evaluations of P. So these are just enough evaluations to fully specify P. It has D+1 coefficients, D+1 degrees of freedom, and I can fully specify it by writing out D+1 evaluations. And let's say as well as 1 point from the field it's defined over R, and my goal is to output P of R. Okay, so that is univariate Lagrange interpolation is an algorithm to do that efficiently. And so the coding theory perspective on what this algorithm is doing is, you can call it either the low degree extension code or the Reed-Solomon code. But if I give you, as my message, P of 0, P of 1, up to P of D, so it's a length D+1 message. And then I think of my code word as, maybe all evaluations of P over the whole field. What this algorithm is doing is it's efficiently computing a single entry of the encoding. Okay, and so this is what's called the low degree univariate low degree extension code. Yeah, when people say Reed-Solomon code, like they might or might not mean this. Like with Reed-Solomon, it's not fully specified how you interpret your message as a polynomial. Like you could interpret the symbols of the message as evaluations of the polynomial, but also maybe instead you interpret them as coefficients in the standard monomial basis or something. And low degree extension code refers very specifically to the interpretation of the message symbols as evaluations of the polynomial. This is the code that arises most frequently in SNARK design, is these low degree extension things, where in SNARKs typically the symbols of the message will actually be like entries of a witness vector or something like that. And so it's as we'll see later, it's very natural to interpret those elements of the witness as evaluations of a polynomial instead of as like coefficients of the polynomial. So this is just a very efficient algorithm for evaluating like a single entry of the low degree extension encoding of some message. Now, one thing to point out before I explain how the algorithm works is this other thing that Reed-Solomon coding can mean, where the message is like the coefficients of the polynomial, say C0 up to CD, and the polynomial now is sum over these coefficients of Ci times x to the I. If I want to know P of R for this thing, it's like very obvious how I can do this in linear time, right? So, to compute P of R, what I can do is compute, 1 comma R squared, R cubed up to R to the D, and in total, I can write down all these values with just like D or D minus 1 multiplications. And then given all these values, I can then compute, I can multiply 1 by C0 and then add to it, C1 by R, C2 by R squared, and so forth. And so in the end, this would be, D plus 1 multiplications, and I don't know, D or D plus 1 additions or something. And so the total, time to evaluate P of R in this case is, certainly it's order D, field operations, additions and multiplications, looks to me like it's roughly 2D multiplications and D additions, but whatever. So, if I were interpreting the message symbols as coefficients of the univariate polynomial, it's like very obvious how to evaluate that polynomial at any desired point. If I interpret the message symbols as evaluations of the polynomial instead of coefficients, it's less obvious. But nonetheless, we can do this in the same runtime asymptotically, order D time. And univariate Lagrange interpolation is just an algorithm to do it. So I'm now going to explain to you the algorithm. Okay, and also the way the algorithm works, conceptually, is also just really important in SNARK design. And so let's discuss. I guess maybe I'll pause here, see if anyone wants to ask any questions about this. Okay. Question?
One question. Is Lagrange interpolation the only way, or there are other ways as well?
There are probably other ways. It's certainly the most natural way. But no. Let's say there are other ways. So Lagrange interpolation. Let's come back to that question after we see how it works, I guess. But no, it's not the only way. But I think it's the simplest and most natural. And ultimately, you can't really improve the speed. Certainly not by more than a constant factor, just because even reading the description of the polynomial takes linear time, and the algorithm runs in linear time. Okay. Other questions? Okay, so just ask that question again when we get through this. Okay, so we're given P of 0 up to P of D. And by the way, it's more general. I don't really care that the inputs here are 0 up to D. Really, any D plus 1 points from the field will work. So as I described the algorithm, there's going to be an obvious way to. I'm never really going to exploit that the points, are 0 up to D. It just makes everything much more concrete and simpler. And in particular, in SNARKs, for reasons we've already discussed today, often the D plus 1 points are actually like the D through to unity or something like that. And they're not 0 up to D. They're other point, another set of D plus 1 points in the field or something like that. Okay, so I'm going to let's see. If you know a little bit of linear algebra, what Lagrange interpolation is doing is it's expressing, it's interpreting P0 up to PD as coefficients of P, but in a different basis than we're normally used to. So normally the basis we're used to is what's called the standard monomial basis. And, that's the basis I was discussing, where I said, if we were interpreting the symbols of the message as coefficients in the standard monomial basis, it's very obvious how to evaluate P of R in linear time. So with Lagrange interpolation, we're just using a different basis. And so what is that basis? So we're still interpreting the message symbols as coefficients, just a different basis. The basis is called the univariate Lagrange basis. Okay, and so the first basis element is going to be, let me call it the zeroth. So it's the unique degree D polynomial that maps 0 to 1 and 1, 2 up to D to 0. Okay, so it's like an indicator function. Yeah, that's it. I'll tell you. I'll give you an explicit expression for the this Lagrange basis element. But in general, the ith Lagrange basis element, Lagrange basis polynomial. In the standard monomial basis, the ith basis element would be x to the I. But instead, now we're going to do the unique degree D polynomial that maps I to 0 and all other elements in the interpolating set. So all other inputs in 0 up to D, I to 1 and everything else to 0. Okay, and so let me give you an explicit expression for the 0th Lagrange basis polynomial. Okay, so let me call this L0 of x. Okay, so L0 of x, right? So we want to kill 1 up to D. Yeah. So this is how we're going to make sure that inputs 1, 2, 3 up to D map to 0. We have x minus 1 times x minus 2 up to x minus D. Okay, that makes sure that 1 maps to 0, 2 maps to 0. Because you'll get you'll be producting together a bunch of things where with one of the things being 0, so you get out 0. And so this is almost, I'm not done defining it. This killed 1 up to D. Yeah. The reason we're not happy yet is because if this were the definition of L0, then L0 of 0 would not be 1. Rather, it would be under this definition, this would 0 would map to -1 times -2 times -3 up to minus D. Yeah, which we want 0 to map to 1, right? So all we're going to do is we're just going to divide by this thing. We're going to, this thing up here that we just divide by it so that 0 maps to 1 rather than to that thing. So we divide by 0 minus 1 times 0 minus 2 up to 0 minus D. Okay, that's it. That's L0. Okay, and similarly, like L1, we want to kill everything in 0 up to D other than 1. So we'll have x minus 0. We won't have x minus 1 because we don't want to kill 1. To map 1 to 1 for L1. But we'll still have x minus 2, x minus 3 up to x minus D. And then, again, in order to make sure that 1 maps to 1, we need to divide by, whatever this numerator maps 1 to, which is 1 minus 0 times 1 minus 2 times 1 minus 3 up to 1 minus D. And so hopefully you get the idea. So the ith Lagrange basis polynomial is going to kill everything except I. So, we have x minus I minus 1, but then we don't kill I, we skip it, and, but then we kill I plus 1 up to D, and then we divide by whatever this numerator would map I to, which is like I minus 0, I minus 1, I minus 2, say I minus D. And to be clear, we skipped, we do not divide by 0, so we do not have an I minus I term here, yeah. So those are Lagrange basis polynomials, okay? And here's a little fact, if you want to know what, if I give you P0 up to PD, then this P, the unique polynomial of degree D that, takes this evaluation at 0 and this evaluation at 1, and this evaluation at D, is just the following. P of x is sum over each of the Lagrange basis polynomials times P of I. So if maybe it's clearer if I call these M1 up to MD. M0, M1 up to MD. So just so I don't have a definition of P in terms of P, what that refers to P. Yeah, and so what's going on is if, so this is clearly a degree D polynomial because each Lagrange basis polynomial is degree D. Each Lagrange basis polynomial is multiplied by a constant mi, which doesn't increase the degree. And if I sum up a bunch of degree things, I still have a degree D thing. So this is clearly a degree D polynomial. And if I feed in to it, some number I, where I is in 0, 1 up to D, like what does the sum do? Well, every single, if I look at Lj of I, where j does not equal I, it spits out 0. So what's happening is every term of the sum is evaluating to 0 except for the ith term of the sum. And with the ith term of the sum, Li of I spits out 1, and the ith term spits out, and that gets multiplied by mi. So, that's what's going on here is like, if I evaluate each term of the sum at I, every single term is 0 except for the ith term of the sum, and that term is mi. And so I get the exact behavior I want point by point, where the ith input maps to the ith entry of the message I'm encoding. Okay, questions at this point?
Really small
I
question.
have one question
Go ahead.
about the degree of P.
Mhm.
I take some example, and sometimes the degree of B is not D. Sometimes is less,
It can be
Mhm.
lower, yeah.
and
Mhm.
yeah. So I think it's at most D, but not all the time is exactly equal to D.
Yes, that's right.
Because the
That's right.
sum, yeah, well,
That's right. So you could have, while each Li is of degree exactly D, when you sum them all up after multiplying by mi, you could, get weird cancellations, and the resulting sum is degree less than D. So that's totally correct.
thank you very much.
Yeah. So the Li's are degree exactly D, but P itself might be degree less than D. Yeah. And it's a nice exercise to, like, take your favorite degree 2 polynomial and then write out 5 evaluations of it, and then do degree 5 Lagrange interpolation and see that what comes out is actually degree 2. It can be nice to just work that out, get a little intuition that way. Other questions?
I just wanted
Maybe
to.
I have just one smaller question on so if we take the canonical basis, for example, 1x squared until x to the d, and normally the Lagrange basis is a basis, so we can construct the matrix. Let's say matrix, la matrice de passage. In French, we call it matrice de passage from one basis to another basis. I don't know what is the cause, but because sometime in the implementation, the polynomial are implemented in the, let's say, the.
Yeah.
This is my question, just a question of cost.
Yeah, that's a great point. And so let me address it. So for some reason my pen just died. Let's see if it comes back. So yeah, what an alternative to Lagrange interpolation. I have no idea why my pen just died. So I'll just say this verbally and keep hoping the pen comes back. An alternative is to take your message, which you can think of as lifting the coefficients of the polynomial in the Lagrange basis, and transform it into the coefficients in the standard monomial basis, and then apply the kind of obvious algorithm we discussed before to evaluate, any polynomial in the standard monomial basis at a desired point. Okay. The problem is, and this is why you're asking about the cost, that transformation to go from the Lagrange basis coefficients to the standard monomial basis coefficients, or vice versa, that requires an FFT. And so that cost is like d log d, and has some other gross computational properties. So it's superlinear time. So that basis transformation would be much more expensive than just running univariate Lagrange interpolation directly. Does that make sense?
Thank you.
Yeah, great. Thanks for the question. Other questions?
I mean, as I asked, like, is Lagrange the only thing, or are there any other ways?
Great. Okay. Yeah. So this discussion we just had was roughly how I was going to answer this. So, obviously one thing, like all that's important here is, as we'll see, I haven't gone through the whole algorithm yet. I've given you the key sort of algebraic expression, but now, still I haven't told you how do you evaluate P of R. But we're going to see how you evaluate P of R is you evaluate Li of R for each Lagrange basis polynomial I, and once you have those evaluations, it's very easy to compute the sum in linear time. So all that's really important here is that we can, that the Lagrange basis is a basis such that we can evaluate, every basis polynomial at R, the desired point, in linear time total, in order R total time.
So it's not required that we be able to construct the basis in linear time.
Right. And in fact, if you literally explicitly wanted to write down, like each of these basis polynomials is a degree, D polynomial. And so if you literally wrote down all of their coefficients in a naive way, there'd just be D squared coefficients across all D of them. And that would be, quadratic time. So we're never going to actually literally, write down the polynomials. We're just going to evaluate each one of them at R. So yeah, I mean, there are lots of other things you could do, but I think most of them would ultimately be sort of indirect and silly. Like you could, as we discussed, you could instead transform, the coefficients in the Lagrange basis, to the coefficients in the standard monomial basis, which is another basis that has these properties that you can evaluate each basis element at R in sort of linear total time across all D evaluations, one per basis polynomial, and then apply the same algorithm, but like over that basis, and that like evaluate using that basis. But it'd be silly, because this transformation from the Lagrange basis to the monomial basis is much more expensive than just directly getting the evaluation out of the Lagrange basis.
I'm
So yeah, it's not
confused
the
because
only way. I think it's the most natural way. Yeah.
It seemed like your explanation of writing out the Lagrange basis would take D squared time, but how do you evaluate D polynomials without sort of writing them out?
Yeah, that's great. So that's what I still have to cover. And I will do that as soon as I make sure there aren't more questions. Yeah. You have to be a little clever, but it is just an analog of like, go back to the standard monomial basis, which is, x, 1 comma x squared, x to the D. And, what we said was once I have R, which is the evaluation of this basis polynomial at R, with one multiplication, I can get R squared. And then once I have this one, with one more multiplication, I can get the next one. And with one more multiplication, I can get the next one. So, it's like the dumb way to have evaluated all D. Yeah, that's what's going to happen. If you're completely dumb, you would evaluate this one independently of this one, independently of the next one. And that would take time, like 1 plus 2 plus 3 up to D, and that would be, like about D squared over 2 or something. That would be awful. But you don't have to evaluate them independently. You can reuse work between basis polynomials.
Thanks.
So is that like taking a few terms out of L0 and adding something and then?
Yeah, that's exactly what we're going to do. Okay. So let me just dive into it now, I guess. Yeah. So, with the Lagrange basis, it's like, a little bit grosser than the standard monomial basis, but, ultimately it's the same thing. So the key point is, before I dive into slightly gross algebra, the key point is like given Li of R, with, a handful of field operations, I don't know, like 6 field ops. I don't know exactly however many it is, but it's some constant. I can determine Li plus 1 of R. Right. So in that way, I can, get L0 of R. This will take, D field ops just to get L0 of R, something like that. But then, then I can get L1 of R with like 6 more field ops, L2 of R with 6 more, and so forth. So in the end, I spent, D just to get L0, but then order D, like 60 or something to get the rest, which is order D total. So it's still linear time, but it's probably like the hidden constants hidden by the big O is probably slightly larger than in the standard monomial basis. Okay, so let's write it out. Like just looking, remember Li of X was, so we had to kill everything in the interpolating set besides I. So, so we skip over killing I, but then you go up to D, over I minus 0, I minus 1, 1, well, I minus 1, which is just 1, I minus I plus 1, which is just minus 1, up to I minus D. Okay, so that's the ith Lagrange basis polynomial. And so the way you have to think of it, so if we already have this evaluation, right, I've been given, the product, all right, so maybe I'll just give you a fact, so Li plus 1 of X, okay, so what happens to the numerator when, rather than skipping X minus I, instead I skip X minus I plus 1. So what happens is, with Li of X, I did not have an X minus I factor, but now I do. So Li plus 1 of X, it's the same as Li of X, except, right, in the numerator, Li of X did not have an X minus I factor, now I do. Li had an X minus I plus 1 factor, and now I don't. Okay, so that captures the changes to the numerator. And then what changes in the denominator? In the denominator, every time I see like an I minus 0 or an I minus 1, I just replace I with I plus 1. So I minus 0, becomes I plus 1 minus 0. And, I minus 1 becomes I plus 1 minus 1. And I plus 1 minus 1 is the same as I minus 0, right? So what's happening there is, everything kind of gets shifted a bit. And so I minus 0 gets shifted to I plus 1 minus 0. Okay, but then everything else I see is like the same as before, so again, like this I minus 1 gets replaced with I plus 1 minus 1, which is the same as I minus 0. I minus 2 gets replaced with I plus 1 minus 2, which is the same as I minus 1. So everything is the same up to I minus D. And I minus D becomes, well, I guess that just goes away. So, again, I warned you the algebra is a little bit gross, but I think I minus D, so we gained an I minus 1 and we lost an I minus D, I think. So that's it. So, writing this out a little more cleanly, I plus 1 of X is the same as Li of X, but I multiply by X minus I and I minus D, and I divide by, this I minus D was like in the quotient of the quotient, so it moves to the numerator. And then I divide by X minus I plus 1, which is in the denominator of the numerator. So ultimately just in the denominator, and this is in the numerator, the denominator. So it's also, I plus 1. So I think this is the right expression. Okay, which means if I already know Li of R, I can get Li plus 1 just by, taking Li of R and multiplying by R minus I times R minus D, and then dividing by R minus I plus 1 times R plus 1. Okay, so that's it. So this is, hence, given Li of R, given that I've already computed this, I can compute Li plus 1 of R, with, I don't know, 2 subtractions and 2, or I don't know, the 4 subtractions, 1 multiplication, and, or sorry, 2 multiplications and 1 division. So whatever, four adds, if I call addition and subtraction the same, two mults and one division. Okay, and so that's how I can get, so L0 of R I can just directly compute by its definition in D time, and then, with this many additional ops, I can get L1 of R, and then with, again, this many additional ops, I can get to L2 of R up to LD of R. And so the last thing I want to discuss is division is actually not a constant time operation, but you have to, if you're just doing division, you have to run something called the extended Euclidean algorithm, and its runtime actually grows slowly, but it does grow with the size of the field, the size of the values you're dividing things by. But it turns out that if I want to do, so there's something called batch division, or people call it division in finite fields. People call inversion rather than division, but it's the same thing conceptually. So if I want to do D inversions, I can do this with actually something like I don't know what the leading constant is offhand, but certainly it's order D multiplications. It might be 3D or something. Maybe even just D, I don't know, and just one division. And the details of that aren't important. I just wanted to mention it. So as a result, I need to do one division to go from L0 of R to L1 of R, another division to go from L1 of R to L2 of R. And so in the end, I do D divisions. And, if I did each one independently, again, it would actually be super constant time for each, which is bad. That would be a bottleneck. But in the same way we reuse work between computing L1 of R and computing L2 of R, we can kind of reuse work between division to do all D divisions at the cost of D multiplications and one division. So this is called batch inversion, or people call it Montgomery inversion. And rather than cover the details, I'll just state it as a fact. It's not hard. It's really not a challenging thing. I just wanted to mention it. And so that's how univariate Lagrange interpolation works. So just to summarize, if I give you P0 to PD, the algorithm works by evaluating in linear time, in order D time, L0 of R up to L1 of up to LD of R, and then computing P of R, because that equals I equals 1 0 to D of P of I times L sub I of R. And so once I have these Lagrange basis polynomials each evaluated at R, it's only D more multiplications and D more additions or whatever to get P of R. So that's univariate Lagrange interpolation. Okay. Questions about that?
Yeah, I have one question.
Go ahead.
Can you instead of dividing and to get from one of the Li's to L
Okay,
J,
I have one more question about the evaluation using the streak of Lagrange basis. So I write something down last week about dividing the polynomial p by the product of x minus e from 0 to d. By r, okay, we will construct a fraction. So we will have p over a big L. It will be equal to the sum of mi over x minus e from 0 to d. So if we can make an evaluation of this fraction in a random value, we will have we'll have a cos d. So the problem is just Schwarz-Zippel lemma for fraction, and it turns around out it exists. There is another version for fraction. I don't write all the proof, but there is some fraction, let's say a polynomial over another polynomial, when it can be equal to a specific value. So it is at most the sum of the degree of the two divided polynomials. So I don't know what you think about it, but I think it gives the same cost of this trick of Lagrange basis.
Yeah, I'm not. I guess. I didn't get like all the context. But yeah, I think the key issue here that makes univariate Lagrange interpolation like a little bit annoying or subtle and not completely obvious is that especially these quotients involve involve like d terms. I mean, the numerators do too, which is like an issue, but it's like very obvious that the numerators have lots of overlap, and it's like a little trickier to see that the denominators have just as much overlap. And Yeah, so if you're completely naive about things and don't exploit the overlap between Li of r and Li plus 1 of r, you wind up spending time d per Lagrange basis polynomial. But once you realize that any two adjacent Lagrange basis polynomials are almost the same thing and just differ in a few terms, you cut out a whole factor d there. Yeah, so maybe that I missed the context of your question, and that doesn't really relate to what you were asking. But it's yeah, I guess it's the best I can say right now.
Okay.
Can I
Can
ask,
you
Thank you. Thank you.
uh,
can I
I'd like
ask
to
you a
ask
question,
about
please?
division. Uh, so uh, division, we always can divide one polynomial to another if it doesn't have um, reminder, and but and we can divide by 0 even in the field. So this gets me to the question: uh, Am I correct that we compute L0 uh, as the polynomial? So um, we kind of write down it as a polynomial, and then we uh, have all the other else numerically as elements of the field. Uh, or does this line, uh, does this boundary of computation lies in another place? I'm sorry if confusing.
I might have missed the question at the last second, but the one thing I can say, maybe I'm answering a different question, but I think it is possible to avoid division if so when you compute L0 of r, right, you would presumably the denominator of L0 of r is r minus 1, r minus 2 up to r minus d. And let me just think for a second. Well, no, actually, I guess I don't see how to avoid division there. So what I was thinking was maybe you could do something like along the way to computing, the inverse of this quantity. You can maybe like leave out some factors, and I'm going to say something. I'm going to wind up babbling for a while, and so I probably should just come myself off. So I'm thinking like en route to computing L0 of r. Okay, it might be possible to get like all of the other denominators you're going to need and just remember them. But even if that does work out, and I'm not going to be able to figure out on the fly if it does, that you would then be storing all of those denominators. And I guess if you want to avoid division, you really have to, avoid even inverting those denominators, which is why it might not work out. But anyway, so that's going to increase your storage requirements beyond what is needed if you care about space. So the univariate Lagrange interpolation algorithm I described to you, I said you would actually write down L0 of r, L1 of r up to LD of r, and like remember them. And then once you remember them, you would then, in linear time compute the sum. But you actually can compute the sum like on the fly, where like, first you compute L0 of R, and then you multiply that by P of 0 and add it to your running sum. And then given L0 of R, it's, very quick to get L1 of R. And then, multiply that by P of 1 and add it to your running sum, and so forth. And so you never actually need to store L0 of R up to LD of R. Now, the one problem with that is the whole batch inversion thing. So every time you do a batch inversion, you do pay one division, and so you can only do the complete batch inversion, like batch invert everything at once that you need to invert. If you store everything that you need to invert. Anyway, sorry, that was pretty rambling. But there's actually some recent developments. Next time we're going to talk about multilinear Lagrange interpolation, and there are recent developments about exactly these sorts of issues in terms of making Lagrange interpolation in the multilinear setting operate in very small space by not actually storing all of the Lagrange polynomials evaluated at R. Okay, I'm going to stop babbling. Perhaps I answered a different question than you asked.
That makes sense. Actually, very explanatory. And the core of the question I had is if we do polynomial division during the algorithm, or is it always just field inversion?
Yes.
Field elementary.
Yeah, this is always just field inversion. So it's like when I given Li of R, when I want to figure out what is Li plus 1 of R, right? I just multiply by these two field elements, and then multiply by the inverse of the product of these two field elements. So
if R turns out to be equal to one of these i's that we have, then we just need to start this over with another basis or with another R with another random element.
Great question. And I always, every time I do this study group, I forget to address that question. So I always say next time I'll address that question, and then I forget. So thank you for asking it. So if you want to know P of R, where R is in 0 up to D, it's funny, like, this univariate Lagrange interpolation algorithm like breaks because you have to like invert zeros somewhere, as you just noted. But this is actually the easy case where you don't have to do anything at all, because by definition that like the input gives you P of R. So just return P of R. It's like it's part of the input to the algorithm.
Wow, that's kind of unexpected.
Yeah. So it breaks the algorithm, but you don't actually need the algorithm in that case. Yeah. So thank you for asking that. I actually, I think every year someone asks that, and I'm like, oh, I should bring that up myself next year, and then I forget it. So yeah.
Thank you.
Other questions? Okay. I think we should wrap up here. I think next time we're going to, I think it's awkward to try to start the sum check protocol the same day we discuss multilinear Lagrange interpolation. So actually, I think it'll be a nice session to discuss interactive proofs and arguments. For briefly, there's not that much to say about them, and then move to, in the same session, multilinear Lagrange interpolation. Which is the analog of what we just saw today, but for multilinear polynomials instead of univariate ones. And then after that, we'll go to sum check.
Professor, can I ask a quick question?
Yeah, please.
So I fail to understand the motivation, like at large, in the sense that in the standard monomial basis method, you were incurring a cost of order of d field operations.
Mhm.
So rather than I mean, in hopes of reducing that, you went to this first evaluations of the polynomial as the message, which you then used to construct this Lagrange's basis, and then again use the same evaluations as the messages again, like as the coefficients, right? So you, so I thought that the motivation to go to this evaluation method was to reduce the cost from order D to something. So I'm not sure what was the benefit of changing the visualization as the message being coefficients to message being evaluations.
Yeah, no, so it's a great question. So that wasn't the motivation. And in fact, up to constant factors, like you cannot reduce the cost of going from the message to, the one element of the encoding, just because, both algorithms, Lagrange interpolation and just, if the message was interpolated in the standard binomial basis, there's linear time. So to even read the message, it's linear time. So you can't improve it. So the motivation is actually from snarks. So basically snarks, like internally, naturally want to use the Lagrange basis and not the standard binomial basis. And why is that? I can go back to the snark I sketched several weeks ago with the quotienting stuff. I think the example I gave was, you have like a circuit that like only has multiplication gates in it, and this is called like a grand product. You just want to multiply a whole bunch of things together. And so the prover wants to prove that it correctly evaluated the circuit, A5, A6, A7, A8. And I said, like, the very first thing it would do in most snarks is commit to a univariate polynomial like G, so that, such that G of I equals the evaluation or like the value of gate I when the circuit is evaluated on these inputs, right? So like, if I assign this gate label 9 and this gate label 10 and this gate label 11 and so forth, then, like G of 9, if the prover's honest, would be like A1 times A2, and G of 10 would be, A3 times A4, just because gate 9 is computing the product of inputs A1 and A2 and so forth. And then the prover would prove that, for each gate I, like G of I equals G of like the first in neighbor of I times G of the second in neighbor of I, and this equality is capturing that, like, the value assigned to gate I is the correct one, and in that way, the prover proves that, he actually correctly evaluated the circuit gate by gate. And then finally, he proved, that like the output, what was it, 12, 13, 14, 15. So then he proved like G of 15 is whatever he claims, whatever the claimed value is. The value assigned to the output is the claimed output. And so this polynomial G, this is the univariate low degree extension of, so if I gave you the vector that just had A1, A2 up to A15, up all of the gate value, all 16 gate values in it, that this polynomial G is its univariate low degree extension polynomial. So if I, so G of 1, G, you can decide how many, depending on what commitment scheme you want to use or whatever, if I write it, you can decide how long you want the encoding to be. So this is the low degree extension encoding of the vector of gate values. So maybe we're dealing with the whole field for the encoding, just since it's a conceptual thing. Yeah, and low degree extensions just arise naturally in snarks. Basically, what the prover in snarks like always does is it commits to a polynomial that like captures the values of every gate in a circuit, or all of the values arising as the prover ran some computer program on a witness or whatever. And the verifier or the prover is ultimately going to do some randomized checks on the committed values, and like at the very end of the snark, the verifier is going to need to know one evaluation of the committed polynomial. And so that's the actual motivation. In like just fingerprinting, where you want to know like are two vectors equal, it really does not matter how you do the encoding, like how you interpret each vector as a polynomial. But in snark, we basically always want our polynomials to be specified via evaluations, because we want the constraints capturing like correctness of the computation to correspond to like evaluations of the polynomials arising. Like that's just how the proof machinery works. So that's where the motivation comes from. So hopefully that made some sense, and it's really good you asked, since otherwise I agree the motivation isn't clear. Like why you care which basis you use. In Snarkland, turns out that the Lagrange basis is like the right basis to use almost all the time.
I have a follow-up question to that, to be honest. Can
Go
you
ahead.
break this term down, like low with respect to what?
Great. Yeah. So the context in different contexts, it can vary. So it's sort of a deliberately slightly vague term. Okay. But typically, the security of your snark will have some, like error term, which is like, either the probability, a cheating prover gets lucky and finds a convincing proof of a false statement or something, or like the amount of work the cheating prover needs to do, to with high probability find a convincing proof of a false statement. This error term will almost always be just like degree of some polynomial arising in the protocol over size of some set or some field that the protocol works over. So again, it's not always like the whole field. Like in Fry, you actually the prover does have to write down the whole encoding. So we have some message again, which is typically like all the gate values in a circuit or something, and we have to write down the low degree extension encoding of the message. That's exactly what Fry does. And in order, since the prover explicitly has to write this down, like you do not want the message to be as long as the whole field. So you'd only evaluate the polynomial over if this has size n, maybe this has size only like 4n. So in that case, like your soundness error, like per Fry query, as I sort of hand waved earlier, per query error would be like n over 4n. So this is like degree over, now it's not the whole field, but it's like size of like the evaluation space or whatever. But then you would drive this down to something so this is like 1/4, but that's not low enough. So that's fine. You would then just like repeat the queries, like 64 times or something, to drive this 1/4 down, to what turns out to be 1/2 to the 128 or something. Anyway, so low degree typically just means like low enough degree so that whatever this error term is, it's noticeably less than 1, ideally cryptographically low. And if it's not cryptographically low, you're going to have to make it cryptographically low by repetitions. That's typically what low degree means. Now, so the higher the degree, the worse your security, basically. So the bigger the field you have to work over, and so forth. Typically in these snarks as well, like the prover time is often like linear in the degree. and the verifier time, depending on your snark, might be like, if you're talking about univariate polynomials, it might be logarithmic in the degree. For univariate polynomials, for if you're using multivariate polynomials, it might be the verifier time might be linear in the total degree. For multilinear, and in this case, the prover time would not be linear in the total degree, but rather like exponential in the degree, roughly. Basically the degree is so small that exponential in the degree is actually linear in the size of the statement being proven. Anyway, so the point is like the degree that is arising comes up not just in the security of the snark, but also in the prover and verifier costs and like the proof size and stuff. And so low degree is a vague term that means low enough that the snark is secure and low enough that the prover is fast and the proofs are short and the verifier is fast to check the proof. And so it's deliberately a little bit vague, but like kind of at a minimum, you want a secure snark, like, an insecure snark, you might as well not have a snark at all. And so at the bare minimum, low degree means like, sublinear in the size of the field or sublinear in the size of this set that you're like evaluating your polynomial over, because that's what ultimately controls the soundness error or something like that. Is that enough color to answer the question?
That is enough color. I just wanted to ask one thing, and I think just as a point of like, correct me if I'm wrong, but the only place that I've seen monomial basis working in the snark land, like at least in practice, is whenever you are in an evaluation domain of some smaller domain, and then you wanted to extend that domain, like basically low degree extension. So you go from the extension to coefficient domain, you extend that, and then you come back via the FFT IFFT route. So is that the correct?
Yeah. I mean, so basically, I think the univariate basis mainly comes up really because of powers of tau, trusted setup, structured reference string is all about the monomial basis. And so, yeah, and basically, in order to use this SRS, which is like everyone's favorite SRS, you need to know the coefficients of the polynomial you want to commit to in the standard monomial basis. But always, like, the provers ultimately naturally receive the polynomial specified in the Lagrange basis because of this sort of thing, where the polynomial they want to commit to is kind of naturally defined by its evaluations, over some interpolating set. And so in order to use powers of tau, you have to first, use the FFT transformation to go from Lagrange basis to monomial basis. And like, in my view, that's like pure waste.
But even if you don't want to end up at monomial basis and you're in a smaller domain and you want to extend that domain, but you're in evaluation domain of something, so you still
I
extend.
will.
Sorry.
So I think, I don't have fully cached how every like algebraic algorithm works, but so often, these algorithms, it's like I give you P0 up to PD, and for I will have you do this, and I'd have to think which other snarks would have you do this. What I need is, as the prover, is to get more evaluations of it. So I want the evaluations at more points. And again, typically they use root to unity, but let's like ignore that or something. And so, I think if I'm understanding you correctly, and maybe I'm not, so please, clarify.
No, this
I
is
think
exactly what you're referring to. The way you do it is by IFFT and FFT.
Right. And so, yeah, but I'm not sure. Yeah. So the algorithms that do this, as quickly as we know how to do it, which is about d log d time, will do an FFT and an IFFT. I'm not sure whether, I guess they may be internally translating, converting from Lagrange basis to monomial basis, the standard monomial basis, and back. Okay, that might be how they work, but like, and and so I think you're probably right about that. But like, you know, that's just how they work, right? Like I'm very happy to they did you know to the prover itself just wanted these evaluations. Like it only cared about the Lagrange basis. And so, you know, the monomial basis might come up in the algorithms that, you know, you black box apply to get what the prover needs. But ultimately what the prover needs is stuff in the Lagrange basis. Does that make sense?
Yeah, that was basically, I think, what I was wanted to put the point across. Like I have only seen them in these black boxes. Otherwise, in the KZG land, where basically you can operate on the monomial basis.
Yeah. So KZG like chooses to operate on the monomial basis. I think just to have this powers of tau setup, and I don't know if you get the same nice properties from your structured setup if you try to directly set things up in the Lagrange base. You know, certain updatability properties some people like. I don't know how. I think you can get those with the Lagrange basis too, but I could be wrong. But at any rate, like powers of tau, as people have sort of settled on that. So now, you know, even if the prover kind of only cares about the Lagrange basis, in order to KZG commit with the powers of tau SRS, you sort of have no choice but to convert to the monomial basis. I can say one other place where this might come up, but sounds like someone might want to ask or say something first.
Professor, so if no one else has a question, I'll just ask one quick question. With respect to justifying the term low degree extension, the low part is there. I believe if I track down the literature, the low degree extension was independently made and like devised or coined way before the snark even came into picture or any of this ZKP thing came into picture. So I'm a little bit confused how the low nomenclature is justified by snark.
So I mean, I don't know the first paper to use the term, but I would have guessed that it would have come up. It came up in the interactive proof literature where you have exactly the same issues, you know, where like the security of your interactive proof. So there's no cryptography in the proof, but there is some probability, like the cheating prover convinces the verifier, you know, to accept when it should reject, and the security is still something like total degree. You know, if you're the interactive proofs all use multivariate polynomials, so it'd be total degree over field size or whatever. I don't. I would be surprised if the term low degree extension came up before the interactive proof literature. If it did, it was just in like maybe coding theory or algebra or something. And then, but even then, you know, the distance of the code is, you know, degree or total degree over, you know, like code word size or whatever. So it's the same thing coming up. Oh, I guess you're asking specifically about why you care about the Lagrange basis. Interactive proofs also care about the Lagrange basis for basically the same reason snarks do. I do not know why a coding theorist would care about the Lagrange basis. That is not clear to me. Coding theorists probably shouldn't care about the Lagrange basis.
Yes, interactive proofs, yes. So that answers what I was trying to ask. Thank you, sir.
Okay. Yeah. So, you know, it's not snarks, and it's all proof systems. So, you know, whether it's a snark, which, you know, which an interactive proof is a component of the snark, or just the interactive proof itself, they all kind of operate in the same way where, you know, the prover, whether it's, you know, using cryptography to commit to these values or just in its own head materializing the values and never actually committing to them, nonetheless, the prover winds up taking these like gate values in your circuit and looking at considering a polynomial whose evaluations are the gate values. So the interactive proofs operate in that way as well. And what we will see more, you know, examples and details of that very soon. As soon as we get to the SumCheck protocol, we're gonna see that, because every application of the SumCheck protocol works in that way. Like SumCheck is all about summing up all evaluations of a polynomial over, you know, Boolean inputs, and so it's all about evaluations of the polynomial. So that's all about the Lagrange basis. Yeah, so it's the proof systems, whether they're, you know, snarks or otherwise, that the motivation for looking at the Lagrange basis comes in. Yeah. Okay, so I guess back to the standard monomial basis, and does it have any like benefits of the Lagrange basis? So there are some polynomial commitment schemes that exploit the following property. So I think I think people only really use these or will use these for multilinear polynomials, not for univariate. So let's let P be a multilinear polynomial. Let's say with n coefficients. Let's not even worry what So that means log n variables. We'll talk next week about all of this. Why log n variables means n coefficients and so forth. So in the n coefficients in the Lagrange basis, and I haven't told you what the Lagrange basis is for multilinear polynomials. Just don't worry about it. Again, it's evaluations of the polynomial over a certain interpolating set. So what some polynomial commitment schemes will use is like, I can write P, if I want to evaluate P at any point, I can actually write that as a vector matrix vector product. Okay. So here we have square root n row columns and square root n rows. Okay, and the entries are just the n, coefficients in the Lagrange basis of P, coefficients of P. Okay, and then these two vectors each have length root n, and these are vectors derived from R. And I won't go again. I don't want to go. I'm not going to go into the details because we barely talked about multilinear polynomials thus far. Okay, and so this structure can be really important. And I'd say, some polynomial commitment schemes exploit this structure, others don't. But this structure generally, if you exploit it, it leads to a faster prover. Okay, and so we'll get into the details of this, several months from now. But anyway, yeah, so what's going on is like you can always write, if P is like univariate in this, you can always write P of R as like the inner product between, let's go back to univariate, the inner product between the coefficients of P and the some other vector, which in the standard monomial basis would just be like evaluations of P, so the coefficient vector inner product, like, powers of R. That's the standard binomial basis. And in the Lagrange basis, it would be, so if the coefficients were instead for the Lagrange basis, it would be the coefficients in a product, like all the Lagrange basis, the vector of all Lagrange basis polynomials evaluated at R. Anyway, so it's always an inner product, but like in certain cases, the multilinear Lagrange basis and the univariate monomial basis being the two main cases, this second vector has extra structure. Okay, so it's all about this second vector, and if this vector has extra structure, you can, rather than writing the evaluation as an inner product between coefficients and some other vector, you can actually write it as a vector matrix vector product. Okay, and that's equivalent to this second vector having certain tensor product structure. So specifically, in the standard monomial basis, if we're talking about univariate polynomials, we can have the coefficients of the polynomial arranged, as a root n by root n matrix, and you can literally write P of R. I'll tell you, you'll just have to take it on faith unless you want to work it out yourself. Like the right vector to multiply on the right has the first root n powers of R, and the left vector has the first root n powers of R to the root n. And so you can, if you'd like, you can check on your own that if P of X is I equals 0 to n minus 1 of Ci times x to the I, that P of R equals this vector matrix vector product. Okay, so all right, I've been rambling. To sum up here, this nice structure that some polynomial commitment schemes use to get a really fast prover, make commitments really, really fast to compute, arises if you work with multilinear polynomials in the Lagrange basis or univariate polynomials in the standard monomial basis. It does not seem to arise if you work with univariate polynomials in the Lagrange basis. Okay, so if for some reason you wanted to have a univariate polynomial-based snark and use a polynomial commitment scheme that exploited vector matrix vector structure in polynomial evaluation queries, you would kind of be forced to use the standard monomial basis. But then the fact that, in snark land, the provers kind of always handed the polynomial on the Lagrange basis would force the prover to convert from the Lagrange basis to the monomial basis in order to apply the commitment scheme that uses the structure. And that may well give back a lot of the prover benefits that you do have once you actually get the coefficients in the standard monomial basis. So anyway, that is one other place that the standard monomial basis for univariate polynomials might shine in snarkland, but with the major caveat that the benefits might all go right away just because, just to get the polynomial coefficients in that basis may well give back all of the nice properties you get once you are in that basis. So, all right, that was rambling, but hopefully useful to listen to. Okay, any last questions?
I have a question about the evaluation cost. So we know that now it's linear, okay. But I don't know if there is I believe that we can do less than linear in N for the evaluation. What's believed in the community? So is there any lower bound, or we can go until the constant time, or
Yeah, I mean,
this
I
is
think
maybe a vague question.
no, it's a good question. I think there's a trivial lower bound until you start assuming certain properties of the polynomial, like sparsity or something, right? So if I read a degree D, so let's say I'm given as input a degree D polynomial and I just don't read one of the coefficients, right? Like if that, I cannot possibly know what the evaluation is at any point unless I read that final coefficient, right? Like if I change that coefficient, I change the evaluation, regardless of the desired evaluation point. So I need to know every single coefficient. Like I just have to at least read the whole input. So that's like a trivial lower bound. But you do wind up with settings in snark design where, maybe it's a degree D polynomial, but only a tiny fraction of the coefficients are non-zero, right? And then you can start asking, like, you do have to read every non-zero coefficient, but it may well be possible to evaluate the polynomial at a point in time proportional to the number of non-zero coefficients rather than the degree. Basically, you get to just skip the zeros and pay no cost at all for the zeros. And that gets to be a complicated question. That gets to be quite interesting. But if you don't have a property like sparsity or something, it's sort of trivially the case that you have to at least read all the coefficients, just because if you skip any one of them, you can totally change the desired evaluation of the polynomial.
Thank you for the answer.
Thanks for the question. Okay. Last chance for questions.
I mean, you said that in the KZG land there's
All right. My my iPad died, so if there was another question, go ahead. I'm now on my laptop. It seemed like there was no questions, but maybe my audio just cut out when the iPad died. Any questions?
just that I heard somewhere that I think from Dan Bonnet that there's powers of tau in the evaluations side of the KZG land as well. So I'm just curious if there exists something like that.
Yeah, so what people have started talking about doing is you can take the powers of tau SRS and you can just process it into so powers of tau without knowing tau. You can nonetheless obtain an SRS that has hidden in the exponents the Lagrange basis polynomials evaluated at tau. Okay. And this is basically because change of basis from standard monomial basis to the Lagrange basis is just a linear function. And because it's only linear, you can actually apply that linear function like in the exponents of these group elements. Like you don't have to know the exponents to, multiply each one by a known constant or whatever. But I generally my personal feeling is like this is not a great thing just because it's very expensive. Like you only have to do it once for all time. But look, it's if you have n powers of tau, the transformation involves doing n log n group exponentiations, and each group exponentiation is itself like 400 group operations, which is itself like 6 to 12 field operations. So, you're talking about, like many, many, many thousands of field operations like per entry in the SRS. And, it's just, even doing that just once is like pretty painful. But yeah, so you can do it. And in that way you can, even if you had a powers of tau SRS, like you could kind of turn it into a Lagrange basis of tau SRS. I'm not, yeah. To what extent people are actually doing that in practice, my understanding, I haven't encountered anyone actually doing that, and I don't know if it's because it's like annoying to make everyone download the new SRS, which is in the Lagrange basis, or if it's because of what I just said about it just being really, really expensive to do that transformation, even though you only have to do it once for all time. But it is an option, and some papers have been invoking that option, like in the paper, if not in the actual implementation or deployment. So yeah, thanks for raising that. It is worth being aware of.
Yeah, thanks.
Yeah. Okay, well, let's wrap it up. It's been been a lot of great questions. So again, next week we will discuss interactive proofs and arguments, like just a little bit about what they are, and sort of details of that are worth mentioning of the models, and kind of what aspects of the models kind of are like matter and what don't. And then we'll talk about multilinear Lagrange interpolation, and after that we're ready for the Suncheck protocol, which is like a real highlight. So I'm looking forward to it. So thanks for sticking around this whole time, and I will see you next week.